Recording is rolling. It's Monday, January 27th. All right, so really I'm just gonna lecture to you guys today. So start new stuff, we start harmonic motion, see how far I can get into waves. Of course, back on Thursday, Friday, you guys did a pendulum lab. Actually, that was really the intro to this topic, right? So harmonic motion, you guys had a pendulum lab, pendulum swing back and forth, some kind of periodic motion. Okay, so what variables are involved? What else? What other situations could be periodic like this? It could be show up on the AP exam. Okay, I do have at least a couple of labs signed up this week. There's going to be spring oscillation. So what if you put a mass on a spring, have it oscillate? You guys see the animation version of that, right? And then this lab I had where using tuning forks and a ruler, you can determine the speed of sound. Usually works out pretty good too, right? So pretty close, right? Your next AP classroom is open. I'll probably change the due date on that, but the harmonic motion one is open. So there you go. All right. You know what? Before I put the PowerPoint. Okay. All right. So what formula is looking at on? Right, so here's your AP equation thing, right? All right. So here's all the rotational dynamic stuff we did. Let's check out these real fast. Right. So you guys see T equals 1/F. What do you guys think T stands for in that context? Not, huh? What do you guys think F stands for? Okay, yeah. Okay, there you go. Yeah, so T is time period. Yeah, yeah. Now, in other contexts, it could be maybe tension. I try to use F sub T for tension, like force due to tension, for this very reason, because capital T, you can say, okay, that could be like a time period. Okay, like time period of oscillation. Like how much time does it take this to go back and forth once? Or like what we did about last week, right? What do you guys think the F stands for?
Oscillation.
Okay, it has to do with oscillation. It starts with an F.
Frequency.
Frequency. Yeah, frequency. Right. Okay, so those would be, do you guys see reciprocals of each other? Right. So, okay, so if it took, let's say it takes a half a second to swing back and forth. It takes half a second to swing back and forth. Okay. How many times per second is it swinging back and forth? Two, and that's the reciprocal. You guys see that's the reciprocal? Okay, so however many times it's doing something per, take the reciprocal. Right, so the time period to do something, how frequently is he doing it? Those are reciprocal questions to each other, right? Hey, look, here's the formula. This was the answer to your guys' lab back on Thursday, Friday, the time period for a pendulum. Now, there's a really similar looking formula right here. It's supposed to do with springs, got mass and springs. So you guys see that? Okay. And we got some oscillation. Actually, they could have done either or here. I'm kind of surprised both on here, but if you made like either a sine or cosine wave, which are the same shape, it just shifted apart, right? What does that look like? All right, so that's on the AP equations, bunch of stuff you guys are gonna see here. All right, so let's open this up. All right, so here's starting point. This is what you guys put together back on Thursday, Friday. You guys remember? Okay, so to remind you guys what was going on. You guys did three different experiments. Yeah, you guys do have notes out, right? You guys got notes out because I'm gonna see if you guys remember how to do some of these graphs that you guys just learned. Okay, so you guys were comparing time period to the starting angle, time period to change out this mass, and time period to this length. If you're changing out length, that's what you guys are doing. Okay, this is the formula that we put together by the end of this whole process. Okay, and then we ran the numbers on your graph and actually work out. So if you did time period versus the square root of length, or actually I think what we did was time period squared versus length, right? Because that would also linearize. Okay. The slope has to do with, well, if you put this 2 pi in the square root of g right here, where they are, right? So it can be 2 pi over the square root of g, or on t squared versus L would be 2 pi quantity squared divided by g, like that. All right. All right. Let's do these 4 graphs here. See if you guys remember those. All right. So you guys got your notes up. I'll draw these with you guys. All right. So let's do some graphs. Because these would definitely be fair questions on AP exam. AP could ask you any one of these and have you scratch or draw from scratch. So there's somewhere on here, but pendulum graphs. So you know what you're looking at. Maybe sketch out a little model, right? That might be helpful. It's got L, got theta, got M, got T for time period. Okay. All right, so let's do time period as a function of mass. Let's do time period as a function of starting angle. time period as a function of length. And I also had you guys do time period squared as a function of length. Okay. Okay. Guys, what's the unit for time period? Yeah, seconds. Okay, so we see a t. Let's put that in some number of seconds. I'm really just looking for graph shapes. Okay, so t squared would be second squared. Okay, but if you plotted points, maybe yeah, you had some coordinates with some numbers. Okay? Mass could be in base SI unit could be kilogram. Angle could be in degrees. Length could be in meters. Okay, so variable unit. Right? Like you guys see it over and over in this class. Right? Variables units. All right, go ahead, draw all four of those graphs. See what you guys come up with. This will be your answer to your lab back on Friday. Okay. Oh. Let's look here. All right, you guys remember what these look like? All right, so as you make this mass bigger, 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 here, I got a bunch of masses right here. If I unhook this string and I go from the smallest one to the biggest one and swing it back and forth, how does that affect time period? Yeah, it doesn't. Okay, so on a graph, say if you have a small mass, it takes some time to swing back and forth. If you have a bigger mass, it takes the same time. Bigger mass takes the same time. Okay, put it all together. It would be like that, wouldn't it? That's what you guys got. Okay. Right, how about from the starting angle? So if you make this 5 degrees, 10 degrees, 15 degrees, let's do 5 degrees, supposed to take some amount of time to go back and forth. How about 10 degrees? Is it the same time? So it'd be like that point right there. How about 15 degrees? Same time? Yeah. Okay. Now, if this was a free response question, I've seen scoring rubrics in the past. Sometimes AP looks for like the angle to be less than 20 degrees. So if you get a pendulum question, just mention the angle would be less than 20 degrees or something like that. Okay. All right, because I think it gets too big, it gets a little wonky. It's not exactly a flat graph. All right, how about time period as a function of length? And here's a big hint: is if you look at your reference page, it says time period equals 2 pi times the square root of L over G. Okay. That can tell you what shape this one's going to look like. You guys, what shape is that? Square root. It is a square root. Right? See, time period is proportional to square root. At 2 pi, that's a constant. The gravity field, well, if you're walking to the surface of a planet, you can also treat that as a constant. Okay? Yeah, it's definitely some kind of square root. Okay? All right, so there's two immediate ways to linearize this. You could do time period versus the square root of length. That would linearize, right? Or you could do what we've got here and what we did Friday, time period squared versus length. Okay? Could I take this and square both sides? Time period squared equals, and then I got a 2 pi quantity squared. Okay. Now I got the square root of g down here. If I square that, it brings back to g. And then times this square root of L being squared is just L. Okay. All right, so what shape does this last graph look like? Linear. Okay. And furthermore, what is the slope of this graph equal to?
1.
2.
2 pi squared divided by 2.
Yeah, 2 pi squared over g. Here's your slope right here. There it is. Okay. Oh yeah.
Why does it become 2 pi squared over g instead of just 2 pi squared times L over g?
Yeah. So it's just the slope. It's like y equals mx. So L's still here. It's just
why did that g shift over?
Okay, because it's the same thing. Yeah. So if I have time period squared equals 2 pi squared times L over g like that, right? Okay. That's the same thing. This is the same thing as this 2 pi 20 squared times L over g. T pi squared equals 2 pi 20 squared over g times L. Every single one of these is the same thing. Yeah, so they're all identical. Right? The reason I shuffled the g over is so that I could just have the L as its own x-axis variable, right? And then the g, I can think of that like a constant, because if you're just locked in the surface of a planet, that would be a constant. So I can tie it into the 2 pi squared, and then that's could represent the slope of that line. So it's gonna be, yeah. All right. All right, so you guys got those graphs? All right, look over here. All right. All right. Now this is a little bit beyond the scope of this class. AP won't actually this exactly probably, but I want you guys to see a connection here. So, okay, so this is non-Bob pendulum. The pendulums that we have in this class, we're going to assume that the string itself has negligible mass and all the mass is in the Bob, right? All right. But in the real world, right, you might get something. Actually, one of your textbook questions, if you read your textbook questions over the weekend, because I gave you guys the page, right, has this exact question. That's where I got this from. You put a hanger on a doorknob and it swings back and forth. Right? Well, the mass is not just in a nice consolidated bob and there's a massive string, right? We got something like this. Right. So here's a more general formula. Right. Now, what I want you guys to see though is that this does simplify to the pendulum formula that you guys derived back last week and we just went over. Um, if you pop in the appropriate value for I, okay? Because guys, let's go back about 2 weeks ago. What is I for a point mass? MR squared. You guys remember that? MR squared? Okay. In this case, wouldn't R just be equal to the length of the string L? Right. So let's do a substitution right here. In place of this I, do ML squared, right? Rotational dynamics, ML squared. Okay. Guys, would the L squared and then L down here, one of those L's cancel?
Yeah.
Okay, so that goes away. Okay. And then, okay, but there's still one L hanging out, right? Because ML squared, And then, ooh, does the M and this M cancel? Okay.
Like the last one.
Right. Mass in total ends up canceling out. Okay. And so what you have is 2 pi square root L over G. Which is exactly formula for just a conventional pendulum, right? Single pendulum. All right. That's what I want you guys to see there. All right. The kind of connections I want you guys to be able to make from this class, right? You can see the big picture, see how things connect. Okay. All right. Here's the other main oscillating scenario. Especially if you guys are starting to read your AP classroom questions, there's two main kinds of questions. I mean, there's some other ones. I've seen questions like if you have like an iced tea bopping up and down in a glass of water, or you can have different oscillating scenarios, right? But mostly it's either a pendulum or it's a block on a spring. Okay? That's the vast majority of these questions. Okay, so what we got going on here? This looks a lot like the formula you guys know for a pendulum. Instead of the length of the string, now it's this mass you put on the end. Okay, so that matters. And instead of gravity constant, it's the spring constant. Okay, so it's definitely got some analogous parts, right? Makes sense. Now, interestingly, what does not matter? Here, maybe I'll put this as a question. Suppose you have this system up. Or this will be a lab we'll do later this week. Put a mass on a spring, pull it back, let it go. Take some time to go back and forth. You guys see that? Right? Suppose I took this to the moon, where there's a little bit of gravity, but not very much. A little bit. Okay. All right. Would this take more time, less time, or the same time to oscillate back and forth? Same time. How'd you know it was the same time?
Because still a spring has no spring constant, so it's going to balance no matter the gravity.
Yeah, same mass, same spring constant, and the gravity field, not even part of the equation. Is it? Yeah, so this would be the same. This would also be the same if you turn this horizontal and have a frictionless tabletop. That's another setup they have. If you just take this whole thing, turn it 90 degrees, so it's horizontal instead of vertical, it's horizontal. Okay, it's on a frictionless surface or an air hockey table surface. It's the exact same equation that applies, right? So in that case, the gravity field wouldn't even be driving the motion, right? It'd be perpendicular. Okay. Let's see. Oh, there's something else I want to say about this. It slipped my mind. Okay, well, I might have to come back to this one. Okay, walk on a spring. Right. Okay, so pretty soon I'll give you guys a lab. Looks about like this. Right. Oh, I remember what else I want to say about this. All right, it goes like this. This was a free response question. Even either last year or the year before, this was a free response question. They said, oh, you have a spring and you want to determine the spring constant and you only have a stopwatch. That's your only measuring tool. Okay. Because guys, there's a couple of main ways to determine what's the spring constant of a spring. Okay. Last semester, what was the way?
Times X.
Yeah, F equals KX. That was Hooke's law, right? Okay. And some of my students told me, oh yeah, I just use Hooke's law. This was their lab write-up. You guys remember you're going to get a lab write-up? Okay. So last year or two, they got this as a lab write-up. Right. Okay, so say, oh yeah, I just use Hooke's law, F equals kx. I said, well, okay, well, I'll set up an experiment where you hang a block from a spring, and then you hang on a bigger weight, and then you hang on a bigger weight, and then you pull out a ruler and you measure it. Okay? But AP was not given credit for that because you were only allowed access to a stopwatch, not a meter stick or a ruler. Right. This is what they were trying to funnel everybody towards. This is the other way to determine spring constant. Okay? Is you pull it back, let it go. Okay? So do you guys see like the stiff of the spring? Guys, the stiff of the spring is that can be more or less time to oscillate back and forth. Less time. That should make sense too, right? Okay, so bigger K here is going to be smaller T here. Okay? The spring is really stiff. But if it's not very stiff, it's a right? Okay.
So you can figure this out by taking the time and the mass that you put on it to get the K.
There you go. Yeah. Yeah. So put on different masses, put on different times. I bet you could, yeah, definitely make a graph out of that. AP might want you to do something with the slope of a graph. Okay.
So it doesn't matter how far you pull it down or.
Oh, yeah, that's another good observation too. I'm glad you mentioned that. Yeah. It doesn't matter the amplitude. It doesn't matter how far you pull it. If you pull this 1 centimeter or 2 centimeters or 3 centimeters. Right. Okay. Now you might want to mention that in a write-up just to cover your bases, but you're right. That ends up not being part of this equation either. Yeah, it's a good observation too. Okay. Now, some other things might matter with amplitude, whether you pull it 1, 2, or 3 centimeters. Maybe like the maximum speed of this block going through the equilibrium point, as going back and forth. Right, like that could change, but that's not what this equation says. You're right. So the amount of time overall to go back and forth would be the same. Yeah. All right. Was there another question too about this one? Or okay. All right. So you guys good? All right. All right. So all right. Okay. So when I eventually have you guys do this lab, I think I'll probably have you guys make all these graphs. I think. Okay. So yeah. So just look for these. Right. Oh, and this last one, hey, look, like it's an oscillation type graph, right? So I've got a better slide for that too, but you guys will see that. All right. So if this is either oscillating up or down, or here's the horizontal version where it's going right left, maybe I should put a frictionless surface underneath this. Okay. The position versus time graphs are going to follow either a sine or a cosine curve, which is the same shape. So kind of pick your favorite one. Okay. And sine or cosine, well, that could tell you how high up or down or how far lateral right or left you are, say on a unit circle, right? Okay. So if you have these two blocks oscillating, and say you watched a car go around a circular racetrack, sometimes we see this called phase space. Okay. Do you guys see these coordinates, like these dash coordinates, could exactly pinpoint the car all the way around? Because it's the same thing. Right? One could be a sine graph, one could be a cosine graph, and the position of the car around the circle could be described exactly by that motion. Okay. Right. Car going around constant speed on the circle. Okay. All right. So this one's I'm just setting up some definitions for the next slide. All right. So now these top two you guys saw earlier today. So frequency is 1 over time period, and time period is 1 over frequency. Those are reciprocals of each other. Okay. So here I'll give you guys an example. Suppose you hear this. Okay. Could that be 1 beat per second? Okay. Now 1 beat per second, the time period between beats would be 1 second. Okay. And beats per second has a name. It starts with an H. Does anybody know what it's called? Hertz. Yeah, hertz. Could describe a frequency. All right. So time period of 1 second is going to correspond to a frequency of 1 hertz. Is it? Now, what if you hear something like this? That's closer to 2 beats per second, maybe. Right. Okay. So 2 beats per second. How many? Could you call that 2 hertz? 2 hertz. Is that okay? Okay. And how much time is there between beats? Half a second. Right. It's 1 over 2. What if you hear something like this? Pretty close to 4 beats per second. Okay. Is that 4 hertz? Okay. And what's the time period between beats? A quarter of a second. Yeah, 0.25 seconds. Okay. Guess it. All right. Now this one down here. Now you guys seen omega. In the past, we've talked, omega, that's angular velocity. That's how fast is a turntable turning. Not in this context. Okay, so when you open up this chapter of a physics textbook, and sometimes different textbooks use different characters, so be ready to feel something like that. But I've seen omega also used for this is angular frequency. Right. So this is just going to help set up some graphs that we're about to look at. I think next slide coming up. So, oh yeah, go ahead.
Would the angular frequency be how many times it spins in a second?
Okay, so you just take regular frequency, right? So which we just talked about, right? So if it's 4 beats per second, we'll call it 4 hertz, right? Just very simply multiply by 2 pi, and it's sort of a middle step that's going to help set up the next graph, okay? Your next set of graphs. Okay, again, this could apply to either, here, I got a pendulum here, I got a block on a spring. Those are your two main oscillating type scenarios.
So what's the bit on that?
For angular frequency, yeah, hertz. It's hertz. Yeah, and hertz works out 1/seconds. Yeah, so 1/second. It's really cycles per second. Okay, so 1/seconds. So time period is in seconds. 1/that is hertz. Okay? And then times 2 pi is still hertz. Okay? All right. And so here's your main oscillation graphs. Okay. Now, um, these are all the same type shape, like whether it's sine or cosine, you can just shift those back and forth. They could lie on top of each other exactly right. Okay. So whether you start with the sine or cosine, it's kind of up to you. I start with the cosine because you could start with some kind of displacement. Like if you pull this pendulum from this vertical line and let it go, at least it's starting with a displacement. If I started that with a sine curve, well, I would be starting at the equilibrium point, which means that maybe it was already in motion, which you could do, but like that. Right? I think it's better to start with the cosine maybe, right? So anyway, you start some displacement, you let it go, starts oscillating, or maybe this one starts oscillating, right? And the position versus time could take like a cosine shape, right? So put this whole graph together. I see that x is like my dependent variable, right? So like displacement, right? So how far is this pendulum displaced laterally, or how far up and down is this block on this mass moved, like right vertically? Okay. Okay, so cosine is the main function. Guys, what do you think this A stands for? It's a word that starts with A. Amplitude. Yeah, amplitude. Okay. Guys, if I change this A from like a 1 to a 5, right? Okay, be increasing some by a factor of 5. How would this graph change? How would it be different? Yeah, it'd be stretched vertically, wouldn't it? By a factor of 5. So, like if this intercept was at the point 0, 1, well, now just multiply by 5 instead of 1 here. This go up to 5. And this point down here, this trough could go down to -5. You guys see that too? Okay, and this 0 would still be 0. Okay. Okay, so the whole thing could get stretched vertically. Okay. And you guys see this omega here? Okay, that was the angular frequency I was just talking about. And I put it up here in the right corner to remind you guys, that's 2 pi times the regular frequency. So if you saw this pendulum swinging back and forth or this block on the spring and you counted how much time it took. Okay, so I think last week you guys were getting time periods of somewhere between 1 and 2 seconds to swing back and forth for, it would depend on the length, but something like that. Okay? Suppose it was 2 seconds. Okay, suppose it took 2 seconds to swing back and forth. You have a really long pendulum. It takes 2 seconds to swing back and forth. Okay. What would the regular frequency be? How many hertz? 1/2 a hertz. So 0.5 hertz. Okay. And then could you just very simply multiply that by 2 pi? You get this angular frequency. You get okay. And that would fit in here. Okay. So what was that good for? Why even have an angular frequency? Okay. Okay. It'll help you make this graph because it'll help you figure out what cycles around. You guys know 2 pi radians in a complete cycle. So you can figure out something about the time period. Right? You guys see from this peak to this peak, since this is a time axis that could represent one time period, right? Can you figure that? And it also helps you take rates of change. You guys know the rate change of position. Guys, what's the rate change of position called in physics? Velocity. And what's the rate change of velocity called? Acceleration. Okay. And there's a rate change relationship here too. Show you. Here, I'm gonna pull us over to so I can really point this out. Let me find my physical version of this. Here we go. Right. Right. It's something I want you guys to see is if you hold your ruler flush to the curve, right, that can tell you something about the rate change of that, right? Like if you're walking on a terrain, you got like hills and valleys and you're walking around, right? It's like, okay, well, how flat is the terrain? So at this point right here, right? Okay, this point right here, say I'm holding my ruler flush to the curve, okay? And see how my ruler is flat? It has 0 slope, doesn't it? 0 slope, right? So if the rate change of your position, now this is really at an instantaneous moment. Sometimes it's like a philosophical question because things are always changing, right? But the instantaneous rate change at that point would be 0. So could you say the velocity at that point would be what? 0. Oh, look at that, 0 velocity. You see that? Okay. And then immediately after that, it starts to change. It actually starts to go down, negative. Okay, so could you call that a negative velocity? Okay. In fact, guys, where is it the steepest? Where is it the most negative? Right here? Right here. At this node, you could call it, right? Okay. So that's where it's like the steepest, and it'd be steep negative. You guys see how that aligns right there? Like the most so the greatest negative velocity. Okay. Now after that, it's still negative velocity, but it's not as negative. Okay, so then the coordinate of velocity versus time becomes close to zero. Okay. And then when you hit this point right here, guys, what's the slope of this curve at this point? Zero. Call that zero velocity. So like right here, again, that's only for one instant. Right? Kind of like you throw a ball straight in the air at the very top. Okay. And after that point, look at that. You guys see this goes back positive again. Now I got these positive slopes. Right? That's going to correspond to a positive velocity. Okay? And you can take that same pattern and go from velocity to acceleration. Okay, so actually about half you guys are calculus. Yeah, have you guys run into this? You guys have probably taken a derivative of a sine curve, right?
It looks like the unit circle when you put it on a graph.
Yeah, sure does. Yeah. Okay, yeah. So maybe from trigonometry, you guys seen that? Okay. Okay. I don't know. I've been in a calculus class a long time, so I don't know. Maybe the order they teach these things. Maybe it's coming up soon. Okay. So probably at some point you're going to take the rate change of a sine curve. And guess, let's just start with sine. Guess what's the rate change of sine? Cosine. That could go from velocity to acceleration. Guys, what's the rate change of? Go back to the top here. Cosine. Negative sine, it is. Aha, right? And then negative sine, the rate change of that could become negative cosine, and the rate change of negative cosine goes back to positive sine. It's a four-part cycle, right? So once you guys got the sine to cosine, cosine to negative sine to negative cosine back to positive sine. All right. Oh, it's a four-part cycle. It goes round and round, right? Okay. Do you guys remember? I may have mentioned this once last semester. Does anybody know what the rate change of acceleration is called? Starts with a J. It's called jerk. It's called jerk. Right. So this could also have a jerk graph, maybe. Right. These could just repeat forever, right? Something like that. Okay.
So if that's the sign of like a curve, where would the beat be made? Would it be at the peaks or the valleys, or where would the beat be made if that was the sign of the
Yeah. So it's wherever whatever corresponding part looks the same. So it could be like all these peaks right here. So it could be like beep, 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 something like that. Right. Okay, so take one full cycle between beats. Yeah. So we have like that. Beep, 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 something like that. Oh yeah.
For that X graph, when it hits the line, is that the point of equilibrium?
Yeah. So like this point right here could correspond to like this point right here, right? And if this mass is oscillating like up and down, up and down, up and down, maybe it eventually settles at some point. Yeah, that could also represent the point that it eventually settles at. Yeah, that's true. That's true too. Right. All right. Now the other thing here is so you tell the full story of what you do with this angular frequency omega. Right. You guys see every time you take the rate change, one of these omegas comes out, and then take another rate change, and omega comes out again and becomes squared. Okay. If you're in calculus, I bet you know what rule that's called. Starts with a CH. It's called the what rule? The chain rule. The chain rule. Yeah, you guys see chain rule, right? Right. That's a chain rule application right there. Right? Which if I left those 2 pi f, then it'd be a little bit more complex. Yeah, okay, multiply by another 2 pi f, another 2 pi f. Here's just, okay, I was slapping omega. Okay. Take that. All right. Let's put this aside here. All right, let's get back to this PowerPoint. All right, so you guys get so far? This far? All right, so yeah, here's in a snapshot your two main oscillating situations for this unit in AP. You guys know AP loves graph linearization. Right, it's a bunch of stuff we did for at least the pendulum we did so far. Right? So the one we'll do later this week. Okay, so here's a couple of ways that you could linearize each of these graphs. Oh, that's what I meant to ask you guys too. But wait, did I ask you guys this? Yeah, we did this. Right, what's the slope of this line? This is what we came up with, right? Okay, now this is not the only way to linearize this. Right? You could do t versus the square root of L. That would also linearize. The slope would be a little different. You could also take, guys, could I take this 2 pi quantity squared, right, and combine it in the axis? Could I do 2 pi quantity squared times t squared and just throw that all in the axis? And then if I did that, then now the slope would be what? 1 over g. Yeah. Could I swap the axes? Could I put L up here and like 2 pi quantity squared t squared down here? Right? And the slope would just be g, wouldn't it? Right? You do that. And then kind of similar story for block on spring. Yeah. Ooh. Here's a good tidbit to know. Shit, I think I'm gonna do this one from scratch on paper too. Okay. But here's the main question before I switch over is right here. Oh, suppose you got a spring, it's just hanging vertical and there's nothing on it. Right? There's nothing on it, right? Then I'm gonna hang a weight on it right here. And I'm gonna let it go. It's gonna drop to some maximum displacement. You guys see X max all over on the right here, X max. And you let it oscillate back and forth. And after like 100 oscillations, well, eventually frictional losses, it comes to a stop. Some dampening comes to a stop. Okay. Okay. And where it comes to stop is the equilibrium stretch position. Okay. You guys, is the maximum stretch position in the equilibrium stretch position? Is that the same spot or different spots? They're different. Okay. And what I want to convince you guys is that they're different by a factor of 2. Right. So this is a good tidbit to know. Might pick you up a couple of points on the AP exam. Okay. So how could you determine what's the equilibrium versus what's the maximal stretch position? Right. So I'm going to throw a spring with nothing on it. Right. Then let's do a spring. Well, I guess this should be stretched some amount, right? Right. Right. Let's call this equilibrium. Right. And then call this the maximum stretch. Right. And maximum, I mean, is this scenario I just told you guys. You hang a weight and you just let it drop naturally to its maximum stretch, and then it's kind of oscillate back and forth until it eventually reaches equilibrium. Okay. Right. So these are different setups, different formula setups that are going to lead to different answers. That's why you're seeing different stretch amounts. So I'll call this X equilibrium. I'll call this X max. Right. X max. Okay. All right. So here's what's the physics framework for equilibrium? The sum of what goes to what? Force goes to 0. Yeah, sum of forces goes to 0. Exactly, exactly. Okay. So I'm thinking, everybody do a free body diagram on this mass right here. Are there 2 forces? Okay. What's pulling down? What's pulling up? Yeah, mg down and yeah, kx up. Yeah, I guess that would be a tension force. Yeah. Right. So I'll call it kx if it's a spring, right? Right. So like Hooke's law, F equals kx. Okay. And I can say, no, you guys just said this. You guys said the sum of the forces goes to 0. Okay. So kx is pulling up, and this would be x equilibrium, which we're solving for. Okay. Okay. Whoops, well, I'll just say equals mg. I could say minus mg equals 0. I should have done that as a middle step. Okay. But if you solve for x equilibrium, you get mg over k. Right? Okay. So whatever the weight is, divided by the spring constant. Okay, so the more the weight, the more it wants to stretch. The stiffer the spring, the less it wants to stretch. That makes sense too, right? Okay. All right. So we got some value. We could pop in some numbers and get something. Okay. All right. Now the maximal stretch point, let it go, it falls all the way down to something, and then oscillates back and forth. What do you think the physics framework is for this? And it's not force equilibrium. What is it? Energy. Yeah, yes, it is. It is conservation of energy. Okay. So let's set up sum of energy at the top equals sum of energy at the bottom. Okay. Sum of energy here equals sum of energy here. Okay. Guys, at the very top, it has what type of energy? Gravitational potential energy. Right. Notice I'm definitely throwing the word gravitational potential energy. Okay. Let's see what. Okay. Is that like mgh? Except instead of h, can I call it x max relative to the slowest point it's ever going to be at down here? Okay. So I'll call it mgx max. That's what we're solving for. Okay. And at the bottom, where'd all the energy go? Into the spring. Yeah. Right. There's no kinetic. I didn't hear anybody say that, right? Which is good, right? Because it's turning around, so it's not in motion at that moment. Okay? Yeah, it's all in the spring. And what's the formula for energy in the spring? 1/2 kx squared. Aha. Right. And it's the same x. This x is this x. It's both x max. So I guess one of these is going to cancel. Right. And those for software. So times 2 divided by k, x max equals, I got 2mg over k. There we go. Right. Now the answer popped up. So now if you're comparing these side by side, it doesn't matter what numbers come up for m or g or k. Okay, this is always a ratio 2 compared to this. Okay, that's it. Okay, there you go. Right there. All right. All right. Everybody good so far? Good so far. All right. That's the main set of things you have to know for this unit. In the past, I know this has always been the shortest unit, like has the fewest questions on it. I know this pre-designed the exam, but that's probably still the case. I think this probably has the fewest number of questions. Right. If you see anything oscillating, just think about the slides that you guys seen in what first like half hour today. Right. All right. Now I do have a bunch of other slides related to waves. A little bit of context. A few years ago, like before the pandemic, AP used to have a whole section on waves. It's really closely related information, so you should just teach it all together. So everything from here on out is probably not going to be on the exam, but maybe it's just good to know if you're going through a physics class, right? So what are waves? How they know? So this still got this periodic motion, right? This still got a frequency and tone, right? So what's some good stuff to know? So frequency and time period are reciprocals, right? So you know that. Guys, this formula right here, which again, not on the AP exam, but good to know. This is V for velocity, so like speed. What do you guys think this lambda stands for?
Wavelength.
Wavelength. It is. Aha, wavelength, which could be crest to crest, or it could be trough to trough, or it could be this node and then skip a node and go to this node, so you get one full S shape. You guys see one full S shape? Could be. It's whatever is the shortest part of a wave that you could copy paste and it could still make a complete smooth wave, right? That's your wavelength, right? And the amount of time that it takes to cycle for that one wavelength is one time period. Okay. Okay. So wavelength times frequency. There you go. And frequency, of course, is one over time period. Oh, there you go. Okay. Because look how the units play out. Because wavelength, what do you think a unit for wavelength could be? Maybe meters, right? And frequency, okay, that could be in hertz, which is like 1/seconds. Put it all together. Meters, 1/seconds. Is that like meters per second? Oh, hey, that could be wave speed. Right? So you like watch an ocean wave, and it looks like it's got there's some speed that the energy is propagating through the water. Right? Like, even if the individual water molecules aren't really moving that far, they're just like kind of bobbing up and down. Maybe the energy propagation is like has some speed to it. Right? All right. All right. So there's two main categories of waves. Some textbooks have like more, but I think it kind of boils down to mainly these two. Right? They're called transverse waves versus longitudinal waves. Right? So if you ever see anything bobbing up and down, maybe you have a string and you bob it up and down, something like this, right? Where each individual particle just has an up-down motion, but the propagation of the energy is perpendicular to that. Right? We're going to define that as transverse. Longitudinal is like a pressure wave. So each maybe each of these points could represent like an air molecule, for example. Okay? And if there's some wave propagating left to right, each of those particles is also moving left and right. It's just oscillating back and forth left and right. Right? And there's these pressure points set up. Okay? So what do you guys think light is? And what do you guys think sound is? Light. What do you think light is? What kind of wave? Yeah, it turns out it's transverse. Actually, can I prove that here? Do I have? All right. I don't see my polarizing filters right around here. So, well, I might dig this up in the near future. Okay. All right. So, and what about sound? Like, how do you think you're hearing me right now? What do you think sound is? Yeah, it's this longitudinal wave. Right. So, like, there's this pressure. If you can see the air molecules between me and you. Okay.
You could say that, well, because light is particle in a wave, it's the transverse. And you could, by process of elimination, longitudinal explains sound because it's the air molecules and it's a wave that goes through the air molecules.
Yeah.
So if sound is longitudinal, then light has to be transverse.
Huh. All right. Something like that. Yeah. All right. Got that. All right. Constructive, destructive interference. So, oh, usually it's easier to draw transverse waves because you can just like whip off some transverse shape. Right. I got some of stuff here. Sometimes this is a common thing to do too, is to represent a longitudinal wave with a transverse wave, right, even though it isn't, right, because it's really hard to draw a proper longitudinal wave because you got to sit there and draw a bunch of dots and then stand back and say like the dot density looks correct, right? But it's easy to whip off like an S shape. Okay, right, so this could apply to both longitudinal and transverse waves. I got a whole folder of demos here. Let me see if I can find a good demo for this. All right, let's do constructive here. Yeah, you guys see where they meet in the middle? So it's like 5 and 5 centimeters. They meet in maybe like 10 centimeters. Okay, so we'll call it constructive interference. Okay. And then find a destructive version of this. Right. So send a couple of wave pulses. All right, so I got like a positive pulse and a negative pulse. Okay. Now, do you guys see this positive pulse and negative pulse headed towards each other? Right. Positive, negative amplitude. Okay. Now, what do you guys think is going to happen when they meet? Yeah, they cancel out, make it like a flat rope. Okay. And what do you think happens after that? Yeah.
Is that how a whip works?
Uh,
Make the sound.
yeah, there's definitely some wave traveling through the lip, right? Yeah. I think the reason the lip cracks is because it breaks the sound barrier. Is that right? I think. Yeah, it goes faster than the speed of sound. Right.
Because as the wave goes along,
Yeah.
you have to position, and then once it gets to the small area, it goes really, really fast.
All right. Yeah, I think that makes sense too.
Because I know that tsunamis work on a similar principle, but I don't know if it's like a negative or positive.
Towards the water, I think, and it builds up.
Yeah. Tsunami would be like a big old wave coming from the ocean, right? Right, yeah. We'll look at tsunami here in a minute too. But you guys see what happened when these two waves cross through each other? Okay. So at the moment they line up, it does make a flat rope. Yeah, so that flattens out. Okay. But there's still energy propagating through, and it goes ahead and they do just go ahead and cross through each other. Okay. Now something interesting too is, you guys watch the endpoint, and you can see it on the one on the left already. You guys see how it flipped upside down? Okay. Do you think this one on the right side, which is upside down, is going to flip back right side up? Okay, when it bounces off. All right. So, yeah, well, physics details there, right? Okay. Yeah. So let's see. Uh, yeah. How does a tsunami work? Yeah. Well, if you got let's say you got like the beach. Here's like the ocean. Right? You got like little waves through the day. Like tide comes in and out, and it's like waves in and out, right? But if you got like a tsunami, like a huge wave, right? Then maybe that's like something like this building up. Okay. In fact, it could be so big that what you normally see during tsunamis, you guys probably all know this, is that like if you're out on the beach and tsunamis coming, like all the water is gonna recede away from the beach, right? Right. Because it's all like building up here because it's all right, there's this huge amplitude, right? And this whole thing just comes up, right? Something like that. All right. All right. So this is what's used also to define what is a wave versus what is a particle. Because there's this question in physics for hundreds of years. It's like what fundamentally is matter. Like people didn't have atomic theory until like relatively recently. Okay, so like you go back a few hundred years ago. It's like, well, what is light? Is light particles? Is light waves? And there's a complicated answer to that. But uh, something that if something can be categorized as a wave, have this wave property, have like an oscillation and the speed, right? Then you could do something like this. So if you say like cut two slits on a card and put it down to a water tank, right? Have a bunch of ripples going, right? Then okay, they'll propagate out waves, and you can get this interference pattern. Now, if you can do the same thing with light, then that would be evidence that light is also can be categorized as a wave, right? And this is called Young's double slit experiment. Well, the original version of this for light. Anyway, so if you see this interference pattern, something like this. Okay. You know what else I meant to mention too for constructive and destructive interference? Because I'm showing transverse waves, but this could also apply to longitudinal waves like sound. You guys ever worn noise canceling headphones? Okay. So now how does this work? It's not just like there's just a bunch of insulation. It's like an active process. Maybe they're like battery powered and turn them on, right? Okay.
It emits a similar sound to the, I think it's interior ears. That's like the opposite of the sound that's coming from the outside.
Yeah, the opposite of the sound from the outside. Yeah, so it takes the ambient sound, whatever that is, and it just reverses it. So like all the high and low pressure points in terms of sound, right? Okay, and then interferes it with itself. So it's really a fancy destructive interference process, is what noise canceling headphones are. Right. So we got all right. So we got that. All right. Here's later this week I'm gonna have you guys do this lab. So take a tuning fork, which there's some frequency that's associated with the tuning fork. Like all musical notes, there's some fundamental frequency associated with this, right? I think like one of the A notes. I bet some of you guys probably know this. Like, what's the definition of one of the A notes? Like 440 hertz, probably. I bet some of you guys know that, right? 440 hertz. Right? So it'd be like 440 vibrations per second. So if I got my beats per second, like going fast enough, if I did like 440 times per second, it's not like a hum of an A note, wouldn't it? Something like that. Right. So anyway, you have this tuning fork, you strike it. So you're going to know the frequency. And then what do you do this later this week? Is you well, have you guys do is take a PVC pipe, put this in water, and raise and lower the pipe, which is going to change the effective length of this pipe right here, right? And at some point it'll resonate, and you'll hear it too. It's not like as you raise and lower it, at some point it's not like so it's always the same note, the same frequency, but it'll increase in amplitude. You'll be able to hear it resonate. And there's only certain places that will resonate. And so, like this point here, this point here. Do you guys see the picture on the right has like a length of approximately 3 times the picture on the left? Right. Right. So from that you can get the wavelength. So here I'm looking at a quarter of a wavelength and then 3/4 of a wavelength. Now the proper longitudinal wave is all those little dots, but I also whipped off some transverse looking waves just to make it stand out easier to see. Right. And so if you know wavelength and you know the frequency on the tuning fork, you can put that together and figure out what's the speed of sound. You guys remember speed equals wavelength times frequency, right? We did that a few slides ago. There it is. So it's feeding into this formula right here. Okay. See what else I got on this. Here's sorry, it's called kind of messed up. Here's a pipe open on both ends. Say if you had a flute or something like that, or it's open on both ends.
There's like an effect called interpolation, right? Where like, you know, as like as the thing is moving and like the speed of which is moving affects like how you interpret.
Oh yeah, like Doppler effect.
Doppler,
Yeah, yeah. Yeah, I got Doppler effect somewhere in here. Let's see, here's yeah. All right. Well, if you ever tune a string on an instrument, here's the physics of that. If you want to look more into these are all you can download this book. You know, I posted it a few months ago. All right, here's all right. Any kind of music. If you want to make a say a major chord, what are the ratios of the frequencies, right? And how are modern instruments tuned? Like there's a whole story to that. Right. Right. Yeah, here's Doppler effect. Might be a little Doppler effect. There. Yeah, a car goes by. You hear a pitch shift. Okay, like that. Hey, here's what you guys are talking about with the whip, right? Like if you break the sound barrier, go faster than sound. Right, so it's called supersonic, right? Faster than sound. All right, decibels. Yeah, we do pretty good. All right, you guys have a good day. I'll see you tomorrow.